series. They tell us that in mathematics, the word sequence is used in much the same way as in ordinary English. Saying that a collection is listed in sequence just means that it's ordered so that it has a first member, a second member, a third member, and so on. So mathematically, you can think of a sequence as a function whose domain is the set of positive integers. Instead of using function notation, sequences are usually written using subscript notation. So here's what they're talking about. This is the formula for a sequence. A sub n is equal to 3n minus 2. That would be similar to them saying f of x is equal to 3x minus 2. They're just using a different variable, and they won't always use the same one. Like you can see right here, a sub n. Down here they've got a sub k. So they can use different letters. But so that we won't be confused between a function and a sequence, they usually use a subscript down here for it. The domain of a sequence is going to be positive integers, positive whole numbers, because we're going to start with the first entry and then the second and then the third. We're not putting in negative entries or fraction entries or something. So the domain is going to be positive whole numbers. So in example number 1, it says find the first 4 terms of the sequence given by a sub n is equal to 3n minus 2. So if I want the first 4 terms, we're going to call that a sub 1, a sub 2, a sub 3, a sub 4. And it's very similar to function notation in that I'm going to put 1 in the place of n right here. So that means put 1 in the place of n over here. So I'll do 3 times 1 minus 2 and get 1. All right, look at the second one. If I put 2 in the place of n, what am I going to get? If I put 3 in the place of n, what am I going to get? 7. And if I put 4 in the place of n, what am I going to get? 10. So those would be the first 4 terms of my sequence. Now, I can find those by hand. I can also find them several different ways on my calculator. I have a sequence mode on my calculator. So if I hit my mode button, right now my calculator is probably in function mode. So if I scroll down to function and I scroll over to sequence and I hit enter, the highlighting switches from function to sequence, and then I'm in sequence mode instead. When I'm in sequence mode in my calculator, when I hit y equals, I don't have y equals anymore. When I hit y equals, my screen will look like this, where it knows that I want to put in subscripts. So it's saying like u sub n, just like we said a sub n. It's saying u sub n is equal to 3n minus 2. Where did I get the n? When you're in sequence mode and you hit your x button says xt theta n. When you're in sequence mode and you hit your x button, it puts an n in for you because it knows what you're looking for. You also can tell it what you want the minimum n value to be. Like typically we would want to start with 1 and find like the first 5 terms or something like that. So I can tell it to let the minimum value be 1, or if I wanted to find like terms 10 through 15, I could change it. That'd be an easy way to do that. So now if I go to my table, instead of it having x and y, it's going to have n and u of n. And here's those same ordered pairs we just got, right? When we put in 1, we got 1. When we put in 2, we got 4. When we put in 3, we got 7. And when we put in 4, we got 10. So there's the first 4 terms of my sequence. Typically, when I get my calculator to graph something, if it has like 4 sets of ordered pairs like this, we're typically plotting x, y points, and it's connecting all of those to make a smooth curve like a line, right? Well, in sequences, I don't want that. I don't want values in between 1 and 2. That's not in my domain. So for that reason, we also set our calculator to dot mode instead of connected mode. And that way, when it plots those 4 points over there for the 4 terms, it won't connect them because it's not supposed to. So if I hit graph and I trace, then I'll be able to see that my first term is, when I put in 1, I get 1. My second term, when I put in 2, I get 4. My third term, when I put in 3, I get 7. My fourth term, when I put in 4, I get 10. And it'll literally lay those out down here for us. Okay? So, a couple of different ways then that we can do those on our calculator. We can put it in dot sequence mode and graph it, or we can use the table of values. Now, sometimes in our textbook, they'll kind of go around the domain of a sequence, and instead of asking me to start with 1, they'll ask me to start with 0. And, you know, they have a good reason for it when they ask me to do that, but that's not the traditional domain for a sequence. So if I looked at that on my calculator, it's going to give me an error message at 0 unless I come in here and I tell it to let my minimum value start at 0. So I can change it to be able to view that, or I can just plug it in by hand, either one. All right, look at example 2. Here's another one where they asked me give the first 5 terms of the sequence. I'm just going to show you one of these here because our goal was just to show you that if by chance you have more than one n in your formula, you do have to plug in the term 1, 2, 3, 4, 5, whatever. You do have to plug it in for every one of those n's. And so that was what I wanted to stress to you in that example. Otherwise, it works just the same as the others. On the bottom of page 619, they give me the sequence. They go the opposite way. They give me the sequence of terms, and they ask me to come up with an expression that would fit that. Basically, they want me to look for a pattern that would fit that information and create a sequence equation to go with it. Now, we're only doing a very few of these on the homework, so please don't let this stress you out. You might remember from last year that we're going to get formulas for this, right? Like we're going to have arithmetic sequence and geometric sequence formulas. So we will have ways to create these, most of these, later on in the week. So don't get too stressed out about this. They're just trying to give you an intuitive understanding of where those formulas come from by having you look at a sequence of numbers, look for a pattern, and try to create something that would fit that pattern, okay? So although I can't give you like step 1, do this, step 2, do this, step 3, do this, I can give you a list of suggestions to try. So these are the things that I would encourage you to watch for. Look to see if you have a constant difference. If not, look to see if you have a constant ratio. If not, look to see if you have perfect squares or if you have factorials. All right, let's talk about what each of those things mean. Look at our first set over here, 3, 6, 9, 12. When we talk about a constant difference, difference is the answer to a subtraction problem, right? So when we talk about a constant difference, we're talking about 6 minus 3 is 3. 9 minus 6 is 3. 12 minus 9 is 3. I have a constant difference between those terms. If you have a constant difference, D, then the equation that goes with that list of terms, that equation is going to have dn in it somewhere. It may be the whole equation or it may be part of it, but it's going to be in there. So for ours, since it had a constant difference, we know we're going to have dn in our formula, and we know that D was 3. So go back and look at that and see how that formula relates to the numbers that you have in your sequence. So if you put in 1, you've got 3. If you put in 2, you've got 6. If you put in 3, you get 9. If you put in 4, you got 12. Hey, that's my formula right there. Look at the next set. For the next set, we start the same way. 7 minus 4 is 3. 10 minus 7 is 3. 13 minus 10 is 3. Awesome. I have a constant difference of 3. So I'm going to go through and say, I know that my formula has 3n in it somewhere. But 3n gave me 3, 6, 9, 12. I have 4, 7, 10, 13. So what's the relationship between these numbers and those numbers? It's just plus 1, right? So that's all that I would have to add to my formula to get this new list of numbers. So again, that dn is going to be in there somewhere. I may have to add something to it or subtract something from it, but it will be there. All right, look at the next set. 9 minus 3 is 6. 27 minus 9, not 6. So this is not going to have a constant difference. Second thing we said to try then was to see if it had a constant ratio. Ratio is a fraction, right? Division. So we could say 9 divided by 3 is 3. 27 divided by 9 is 3. 81 divided by 27 is 3. Hey, I got a constant ratio for this one. Okay, if you have a constant ratio, your equation is going to have r to the n in it somewhere. So our ratio here was 3. So that means my formula is going to have 3 to the n in it somewhere. That may be the whole formula, or I may have to add or subtract something, but it's going to be there. So if we go back and check, if I put in 1, 3 to the 1 is 3. Put in 2, 3 squared is 9. Put in 3, 27. Put in 4, 81. Yeah, that's my formula. And then they could do something kind of like what they had done over here. Like they could go through and give me 4, 10, 28, 82 if I needed to add 1, or subtract 1, or add 5, or something else. The other thing that they like to do is to use squares. Like if you'll notice over here, every one of these numbers is a perfect square. That's 1 squared, 2 squared, 3 squared, 4 squared, right? So that's another pattern that I can give a formula for, because I could represent that with n squared, where if I put in the first term, I would get 1 squared. If I put in the second term, I'd get 2 squared. Put in the third term, 3 squared. And then again, they'll give me things like down here, you'll notice every one of these numbers is exactly 1 more than these. So again, they could give me something where I have to add 1 or subtract 1 or something of the sort. So if I have something that has a constant difference or a constant ratio, we will learn formulas for those later on in the week that will help me create the formula to go along with those. If it doesn't have a constant difference or a constant ratio, I'm going to be on my own. And in that case, I'm going to want to look for squares, and I'm going to want to look for factorials. Okay, what are factorials? Well, you might remember from Algebra 2 that we represent a factorial with an exclamation point. If you have something like 5 factorial, that literally means 5 times 1 less than it, 4 times 1 less than that, 3 times 1 less than that, 2, all the way down until you get to 1. So we could represent a factorial like n factorial. We could say n times 1 less than that, times 1 less than that, times 1 less than that, until I get down to 1. Now, there's kind of a strange factorial that we have to take into account, and that is 0. 0 factorial is just 1. Example 4, they talk to us about recursive sequences. Recursive sequences. There's a really special recursive sequence that shows up in nature. It's called the Fibonacci sequence. It's really random. If you add the first 2 numbers, 1 and 1 gives you 2. Add the next ones, 1 and 2 gives you 3. Add the next ones, 2 and 3 gives you 5. 3 and 5 gives you 8. You can see. It's not, doesn't have a constant ratio, doesn't have a constant difference. It's really random. Like the probability of that number showing up like one time in nature would be extremely obscure. It doesn't show up one time in nature. It shows up hundreds of thousands of times. It shows up in space. It shows up in the middle of the ocean. It shows up in the middle of a flower field. It shows up in animals. So the cool thing about that Fibonacci sequence is that, let's see if we can get to our page here. The cool thing about that sequence is because it's so random and so difficult to generate, can you imagine being the scientist that started discovering this and finding it all over? So these are some of the examples that they found. You can see here that it shows up in the number of pairs of rabbits in their mating sequence, and they went further into their family tree there to show you it continues going. Then they found it in cows, and you can see here the sightings of the sources. It shows up in honeybees. It shows up in fruit. It shows up in flowers. Probably the most common place that it shows up is in the chambered nautilus, just a little slug that crawls along the beach. And in that shell of the chambered nautilus, you can see it generating here on the website. As that creature grows, it expands into a larger shell and a larger shell and a larger shell, and the dimensions of that shell form the Fibonacci sequence. That animal doesn't know math. There's no way that that animal knows how to generate those numbers. It does it by design. And so the amazing thing is, as we go through, I mean, we could sit here and look at example after example after example of the countless places that this shows up. What's so cool to me is that there's intelligent design all over that, which means there was a designer. So to me, my favorite part of that means that God loves math. I think it's his favorite subject. And that he loved hiding all those little patterns for us like a scavenger hunt to go find and explore. So, such a cool thing to me. So, here's an example of a recursive sequence. It's called a recursive sequence because you have to go back and use additional given information. So, here's the sequence that they give me. And they give me the 0 term in the first term, and they ask me to find a second term. So if I'm trying to find the second term, I'm putting 2 in for k, putting 2 in for k, putting 2 in for k. When I simplify that, 2 minus 2 is 0 and 2 minus 1 is 1. I can't finish that if I don't know what a sub 0 and a sub 1 are. They will have to give me that information. So that's why it's called a recursive sequence, because I have to recur or go back to previously given information. Here's another one of those. If I wanted to find a sub 3, put 3 in for k, put 3 in for k, put 3 in for k. 3 minus 2 is 1. 3 minus 1 is 2. So I would find a sub 1, which was given, and a sub 2, which we just found, was 2, and that gives me my third term. So once you pick up the pattern, and you're like, well, hey, all it's asking me to do is just add the 2 previous terms to get the next one, then I don't have to continue with the formula. I can just continue with the pattern. All right, we talked about factorials. Let's look at a sequence that would involve a factorial. For example number 5, they tell us a sub n is equal to 2 sub n over n factorial, and they ask us to start with the 0 term, okay? So we'll start by putting 0 in for n, put 0 in for n, put 0 in for n. So 2 to the 0 is 1, and 0 factorial is 1. When we go to put in the first term, 2 to the 1 is 2, 1 factorial is 1. Skip down, let's say we wanted to put in the fourth term. 2 to the fourth is 16, so we need to find 4 factorial. 4 factorial literally means 4 times 3 times 2 times 1, right? So 4 times 3 is 12, times 2 is 24, times 1 is 24. Now, your calculator will do factorials, but there are some factorials that you can do that your calculator cannot because you are smarter than your calculator. So here's some examples that just deal with simplifying factorials. If we have 8 factorial over 2 factorial, 6 factorial, right? Here's the definition of 8 factorial, 8, 7, 6, 5, 4, 3, 2, 1, right? 2 factorial, 2 times 1. 6 factorial, 6, 5, 4, 3, 2, 1. If you'll notice, the 6, 5, 4, 3, 2, 1 in the top and bottom cancel out, and all I'm left with is 8 times 7 on the top, which is 56, and 2 times 1 on the bottom, which is 2. And so I can simplify that factorial. You also could write it this way. Instead of writing out 6, 5, 4, 3, 2, 1, you might prefer to just write them as the factorials, kind of like an abbreviated way of writing it. Look at another one. If I have 100 factorial, if I put that into my calculator, it will give me an error message. It cannot do that. It overflows my calculator. But we could go through and say, okay, I know 100 factorial is 100, 99, 98, 97, 96, counting down. And 98 factorial is 98, 97, 96, counting down. So from the 98 on, everything's going to drop out, right? And I would just be left with 100 times 99. So I can calculate that. My calculator cannot. I also can do calculations with letters that my calculator cannot. Like here's our definition of n factorial in the top. N minus 1 factorial just means n minus 1 times 1 less than that times 1 less than that all the way down to 1. So you can see again, all of this cancels out, just leaving me that n.